Okay, we are continuing on here at chapter 10. And last time we started talking about chapter 10, which is about energy. And as we talked about the idea of energy being transferred from one place to the next. So remember that we don't lose any energy, we don't create any energy, but there is this sort of transfer of energy from one location to the next. Oftentimes we deal with the system, and also outside of the system is really the surroundings. And the system could be like your test tube, your beaker, whatever you may be working on. And obviously the surroundings would be everything outside of that. And we oftentimes look at energy as that flow either from the system to the surroundings, or once again, it can go obviously from the surroundings to the system. And as we talked about last time, there's sort of that distinction in terms of how the energy is flowing for a particular situation. In any situation where basically the energy is released, that is usually what is referred to as a exothermic process. And there's really a couple of sort of values of energy that we very commonly see, and we will see as we go through the rest of this chapter. We touched a little bit about it, I think, at the end there, delta H, which is the enthalpy, or the change in enthalpy. And for an exothermic sort of process, the actual value that you get for delta H will be a negative value, which would indicate overall energy is being released. We also calculate something like Q, which is heat. That also would be a negative value for any process that is, once again, going to be releasing that energy. Now, as somebody who does release a certain amount of energy, there will be somebody else that will basically pick up the exact same amount. And in those cases, that is energy that is going to be absorbed. And that is what is known as an endothermic process. And the same sort of energy values actually will be positive if you're dealing with really a endothermic process. So once again, if you calculate delta H, or given a delta H for a particular reaction, and it is a positive number, it would be a endothermic process. If you're given or calculate Q and it is a positive number, that means that that really sort of is absorbing energy. Any questions on any of that there? So one way that we sort of relate energy is through what are sometimes referred to as energy diagrams. And that, I think, where we left off here. These are actually two pictures of energy diagrams. And here on the left, we have an exothermic diagram. And here on the right, we have an endothermic diagram. And remember that in a reaction, we have our reactants that go to products. So remember, our reactants are our starting amounts. Our products are obviously what are formed as a result of the reaction. So when we look at an exothermic reaction, the way we can really know that it is exothermic is the energy of the reactants are always higher than the energy of the products. So in order for those reactants really to sort of get down to make the products, overall heat and energy has to be released as a result of that. And when you look at an energy diagram like this, energy on the left, sort of the reaction progressing to the right, that is always what you will see. The reactants energies are always going to be higher than the products. The net result of that is the reaction will sort of give off some energy to the surroundings, and it will be an exothermic sort of process. And that's a little bit different when we look at endothermic. Endothermic, the energy of the reactants are actually lower than the products. That means that in this particular reaction, in order for those reactants to really get kind of up there, energy actually has to be put in. So reactants got to gain some energy as it goes there. Any questions on that there? Now, if you remember, we talked about energy and sort of it being a state function, and the idea that really the only important thing is sort of where you begin and where you end, and that is really the energy of the reaction, or the delta H of the reaction, If you take the energy of where it started to the energy difference of where it ended between the reactants and the products, as we will talk about in a second, that is really what the change in enthalpy for that particular reaction would be. Here, our energy of our products is a lower number than the energy of our reactants. So if you take products minus reactants, you'll end up with a negative number, which would indicate that it would be exothermic. Same thing here. If we take the difference between where the reactants start and the energy of where the products end, that difference will give us the delta H for that reaction. And in this particular case, if we take our products, which is our final state, it's a larger number than our reactants, which is a lower number. So when you subtract those two, you end up with a positive number. Any questions on that there? Now, another thing that you sort of see on this, and I'll maybe redraw one over here. So if we had something like this. So if these are our reactants, these are our products. What happens in a chemical reaction is essentially all the reactants will essentially break apart. So they're basically going to be breaking apart all their bonds. And what happens is they will start to form new bonds on the other side. And we talked about sort of energy related to bonds, right? So when we break bonds, energy is put in. When we make bonds, energy is released. There's a lot of energy that occurs as this happens. So what happens as the reactants start to proceed up this hill to get to the very top here is we have them starting to break some bonds and they're starting to make some bonds at the same time. So you got these guys that are breaking bonds and making bonds, and to get to the very top here, at the very top, this is sometimes referred to as the transition state. And that hill that everybody pretty much needs to climb to get to the other side, that also is what is known as the activation energy. And that really is the minimum amount of energy needed for a reaction to occur. So the activation energy is really the energy barrier that's necessary for the reactants to really get to the other side. The sort of larger the activation energy, a lot of times the slower the reaction is because it's a bigger hill to get to the other side. The smaller the activation energy, the quicker it can get to the other side. Now, there's really kind of two things that has to happen really for products to be formed in a chemical reaction. There has to be collision, and it has to hit each other sort of in the right spot. And they also has to have this right amount of energy to allow products to form and things to start to break. When you get to the actual very, very top in terms of energy, so that's like the highest point there in terms of energy, that is what is also sometimes referred to, that complex there is a transition state complex. Or sometimes people call it a activated complex. And if something is really high in energy, would you think it is very stable or unstable? It's unstable. So things in chemistry, much like things in life, do not want to be at really high energy, want to be at the lowest possible energy that is able to occur. So that is basically your peak of energy. And it's usually relatively, unstable in a sense. It doesn't really hang around all that long. It's really something that has sort of partially made bonds, partially broken bonds. So what happens is relatively quickly, this guy will then kind of drop down to the other side to make products. Again, it lowers the overall energy of that particular reaction. Any questions on that? Now, if we come back here and look at sort of the comparison of activation energies on these diagrams here, we have our activation energy here for exothermic, our activation energy here for our endothermic. Which one is larger? It is the endothermic one, right? So it kind of makes sense overall. It needs some energy to kind of be put in there to get enough of the reactants to get off and up and over to the other side. Not so much there on the exothermic reaction, as it sort of has excess energy. If you want to think about that, it's able to release it overall. So there's probably going to be a greater proportion of guys able to get up this hill than there would be here. And if you compare the two, probably your exothermic reaction may occur a little bit faster because of that lower activation energy. Any questions on that there? Now we'll talk about it perhaps in a later chapter as well, but sometimes one way that we can sort of speed up a chemical reaction is to add a catalyst. And a catalyst is not a reactant. It's not a product. And it does not get used up. In the reaction. A catalyst is there really just simply to provide an alternative pathway for the reaction to take place, really a more sort of efficient way for that reaction to take place. And ultimately the way it does that and how it's able to speed up a reaction is by finding that sort of alternative pathway. Instead of having to go up that big hill there, it lowers the activation energy. So something, when you add a catalyst to a reaction, by finding that more efficient way for that reaction to take place, it actually will lower the activation energy hill. The result of that is there's a lot more reactants that have enough energy to get up and over to the other side, and the reaction will occur a lot faster. So when we add a catalyst, a lot of times, and most of the time, it is for that purpose, to speed up the reaction. And again, that alternative pathway lowers the energy barrier to get to the other side. Any questions on that there? All right, so here's just a couple of reactions, sort of same idea, energy diagrams. These are our reactants up here. Making water here to our products. And again, overall, our products are lower in energy than our reactants. So that's going to be an exothermic energy being released as a result of this reaction. Down here on the right, it is our mercury 2 oxide, which is our reactants, our starting material, going to our products. In this case, we got to pick up some energy there from the surroundings to come in to allow us to do so. So a couple other ways is sometimes exothermic and endothermic are sort of displayed in chemical equations. Is sometimes they will actually be put into the actual equation. And because a exothermic reaction indicates that energy is being given off, it is considered oftentimes a product. So a lot of times when we have something that's a exothermic reaction, if we do put something into the equation, we would put it on the product side. A lot of times you may just see generically written heat on the product side, maybe not a number. And you'll see it on the product side in an exothermic reaction. Endothermic would be opposite. Since heat and energy is being absorbed, it is considered a reactant. So the left-hand side of the arrow. And that is typically how we will see endothermic ones written. Again, it may just be generically written heat or energy on the reactant side or product side. More often than not, though, in sort of chemistry, a lot of times it's not really written into the equation. It is represented by that delta H. So for an exothermic reaction, you will just see at the end of the reaction a delta H value that is negative, and here you would see a delta H value that is positive. So I would say probably 9 times out of 10 in most chemistry books, especially at this level and the level that you continue on with, they oftentimes will not write it into the actual equation, but at the end of the reaction, they will put either delta H equals this value or delta H equals this value. And once again, the value doesn't matter for delta H. It is the sign that matters. If it's negative, it's exothermic. And if it is positive, it is endothermic. Any questions on that there? All right, so as we talked about as well, heat does transfer from hot to cold. So in this case here, our hot water, which is 90 degrees, would transfer the heat to the cold water. The cold water would gain all that energy, start moving around a lot faster. Its temperature will start to come up. As the 90-degree water starts to lose some energy, it slows down its movements, and its temperature starts to drop. And again, if there's sort of an insulated container, they most likely will meet somewhere in the middle of the temperatures that they started with. If you took 90 and 10, that's 100 divided by 2 is 50 in the middle. So we touched on enthalpy. So let's officially talk about enthalpy and a couple of different ways to calculate enthalpy. Most reactions are carried out under constant pressure conditions, including in the laboratory. Really, the pressure doesn't change all that much in the room that you're sitting in. So enthalpy, which is H, and the change in enthalpy, which is oftentimes how it's recorded, is basically equal to the heat absorbed or given off as a result of a chemical reaction or the system. And as we talked about, since it is a state function, what's important is where you start and where you end. And as we talked about the other day, a reminder that where we start in a chemical reaction are reactants, and where we end are our products. So this is like really initial and final, basically, states. So to calculate the change in enthalpy, one way that you could do it is basically all the products, and you subtract them from the enthalpy values of all your reactants. You find these values in tables. So there is a delta H table in a book, and usually in the back of the book, in the box as well, maybe, but maybe a book as well. And these are sometimes called delta H of formation or delta H of F. And these are just values. You go to this table and you look up the values, and a couple of things, whenever you use a table like this, a delta H table, later on in chemistry, when you take 1B and so forth, you use like a delta S table, delta G table. They're sometimes referred to as thermodynamic tables. You always want to make sure that you look up, obviously, the substance that you're looking for, but more importantly, you want to make sure that you also find the correct state. So is it a solid? Is it a liquid? Is it aqueous? Is it gas? There are different states that have different values, so you want to make sure you always find the correct state. The other important thing is when we look at a balanced equation, we have to take into account how many moles of each of those things are there when you use this type of calculation. So that's also, we're going to go over an example here in just a second on how to do that. So when you add up all your products, delta H values, and subtract it from all your reactants, delta H values, again, if you hit a positive number, overall that reaction is going to be endothermic. And if you hit a negative number, it will be exothermic. So let's take a look at one here, which you might need to add to your notes here. And we're going to do this one together, and we're going to talk about sort of how you go about doing this. So a couple of things. Obviously, this is chapter 10, so they assume you kind of went through the other chapters at this point, which we eventually will. But since we kind of skipped ahead, a couple of things. We've been talking about a chemical equation. Again, left-hand side of the arrow are reactants. Right-hand side of the arrow are products. This is a balanced equation where we have coefficients. And these coefficients are what are referred to as the moles of each of those things. So we could say that there are 2 moles of sodium, 2 moles of water, 2 moles of sodium hydroxide. And if there is nothing written in chemistry, it is assumed that it is a 1, not a 0. So 1 mole of H2 in this case. So that's important because when we do calculate our change in enthalpy, we want to take into account how many moles we have of each of these things. It's kind of like how much of each of these things we have. And that would be 1 mole of H2. By the way, abbreviation for a mole is MOL. So that's also an abbreviation for a mole. They had to abbreviate it some way, so they got rid of the E. So MOL actually stands for moles, and that's the abbreviation. So what we want to do here is we would want to go to a table if it wasn't given to us, and we would look up the delta H of formation values. And again, these are all table values you can find, obviously, in a table in the back of your most chemistry textbooks. And what we're going to do is we're going to find all the values for our reactants and all the values for our products. Once again, making sure that we do have the proper states of each of those things. And if you do so, these are the values that you would get here. The units that for each of these values are kilojoules per mole, and that's why we have the moles there on the left as well. So to calculate the delta H in this case, we're going to take the delta H of the reaction will equal our delta H of our products minus the delta H of our reactants. All right, so to do this, we're going to start on the product side, which is over here. I have 2 moles of sodium hydroxide. So I'm going to take 2 times the value of sodium hydroxide that I find from the table, which is minus 470 kilojoules per mole. And that's really 2 moles there. I'm then going to add it to the value that I find in the table for my other product, which is the H2. In this case, the H2 is 0, which makes it pretty easy. That's going to be plus basically 1 mole times 0 kilojoules per mole. And that basically is all of the delta H values for our products. Any questions on that there? I'm now going to subtract that from all the delta H values from our reactants. So I'm just going to go underneath it here. So for our reactant, we have 2 moles of sodium. And from the table here, also not too bad, that is 0 kilojoules per mole. The other reactant is water. There's also 2 moles of it from the coefficient. And we're going to times it by the value for water that we find in the table, which is minus 286 kilojoules per mole. And that takes care of all of our reactants. Any questions on how to set that up there? So once again, that is all of our products. And all this is all of our reactants. Yeah. All right, so now all we have to do is the math part of it. So we're going to take, in this case, basically 2 times negative 470. And we're going to add it to 0. We're then going to subtract basically 0 plus 2 times negative 286. That gives us a negative value here of minus 368 kilojoules, in this case, for our delta H. Any questions on that? Yeah. No, so usually there's some type of change of energy that occurs because, again, as we talked about, sort of the process of just a reaction, which basically involves breaking bonds and making bonds. There's usually some type of exchange of energy. It could be very low number or high number, but there's usually some sort of difference that occurs. Other questions? Would this reaction be exothermic or endothermic? This would be exothermic, yeah. And again, the only thing that I need to know to do that is it's a negative value. So that's all I need to know about it. Again, the value doesn't really matter. Overall, this reaction would release this amount of energy really to the surroundings when it happens. Any questions on how to do that there? All right, so why don't you try one here, I think. All right, so why don't you try this one here? Calculate the delta H for this reaction. Again, the values there are from a table. Again, do products minus reactants and see what you come up with. You're pretty much just given the reaction or equation. You would go find the table if it wasn't given to you, these values, and look them up again for the correct state. Once again, we want to calculate the delta H of the reaction by taking our delta H of all of our products minus the delta H of all of our reactants. So remember, product side's over here. We do also need to take the coefficients into account. So for CO, we have 16. So our delta H there would be 16 moles times the value of CO from the table, which is minus 110 kilojoules per mole. We then would add it to our other reactant, which is the water, and it has a coefficient of 18. So we would take 18 moles times the value for our water in the table, which looks like it is negative 286 kilojoules per mole. At this point, that takes care of all of our products. We're going to do the exact same thing here with our reactants. So coming to our reactant side, I'll go underneath so I don't run out of room. We have 2 of our C8H18, and that's going to be 2 moles times minus 208, again from the table, plus our other guy, which is 25 oxygens. Good news here is oxygen is 0, so 0 kilojoules per mole. And that will equal 16 times negative 110 plus 18 times negative 286 equals about negative 6908. We're then going to subtract it from 2 times negative 208. And it looks like it is negative 6492. I punched all that in, right? Any questions on that calculation? Once again, this reaction would be endothermic or exothermic? It would be exothermic again because of the negative here. So this would be exothermic. It's a combustion reaction like when you light the Bunsen burner. So kind of the same idea. It's exothermic. Now, one thing that you might have noticed or will notice if you use delta H values is when you go to the table, anything that is really an element in its natural form that is uncombined will typically have a value of 0. So that's why we saw in the other one, sodium by itself is a value of 0, oxygen is a value of 0. So anything that's sort of an element by itself, typically you will find values of 0 for them. Any questions on how to calculate that there? All right. Get on that one, I think. One more in case you wanted to practice then. So again, here we can see this is a combustion reaction. This is our reactants. This is our products. And once again, we see reactants are higher in energy than products, which means, again, energy release. In this case, delta H is negative 890 kilojoules, which implies it's exothermic. And here melting. So this is our reactant. We're melting ice in this case. That's our product. And once again, lower in energy or reactant or product. So as we know, when we do melt an ice cube, delta H there is 6.01. That actually has a special name we'll talk about in a later chapter, but that's sometimes what is referred to as the heat of fusion. This is the delta H of fusion. And that is the energy needed to change the phase from solid to liquid or liquid back to solid. So for water, that occurs at 0 degrees Celsius. It takes about 6.01 kilojoules of energy per mole, basically to change water from either solid ice to liquid water or backwards. You need to remove that amount. It's about 333 joules of energy. All right, another way that we do look at heat and energy is through what is referred to as specific heat. And specific heat capacity is the amount of heat or energy that is needed to change the temperature of 1 gram of a substance by 1 degree Celsius. So there is sort of a specific heat formula. It's in that box there. And this is going to be basically Q is equal to MS delta T. That is heat. our energy. It is usually in units of joules or calories. M is mass, which is typically in units of grams. S is our specific heat capacity. Which is in units of joules per gram per degree Celsius, or calories per gram per degree Celsius. And lastly, this is our change in temperature, which is our final temperature minus our initial temperature. And this is one of the very few things in chemistry where you probably will leave your temperature in degrees Celsius. So you actually won't convert it to Kelvin, but you'll leave it in degrees Celsius when you're doing specific heat capacity. Now, one value that you definitely should know is this one, and it's not negatives. That's just from PowerPoint, so I'll get rid of it there. But the specific heat of liquid water is 4.184 joules per gram per degree Celsius. That's a number that is used a lot when you're doing specific heat, or 1 calorie per gram per degree Celsius. That number might look familiar to you. We saw it earlier. That is the conversion between calories and joules, 4.184 joules. Yeah. So again, that is the conversion that we saw earlier that is used a lot. Q can either be positive or negative. And once again, as we've been talking about, if it is negative, it is exothermic. And if Q here is positive, it is endothermic. Now, what makes really Q positive or negative? Well, typically speaking, the mass is a positive number. S, which is the specific heat capacity, is also a positive number. So really the only thing that determines whether or not your reaction is going to be sort of exothermic or endothermic is the change in temperature. So it's really important when you do the change in temperature that you actually do final minus initial, because that will give you the negative sign if you need it, or leave it positive if it needs to be positive. So you just don't want to take the difference between the two, which is sometimes how it's taught. You really do want to go final minus initial, because that will again give you the negative if it needs to be negative, or again keep it positive. Now, a couple other things. I personally use S. A lot of books do use S for specific heat capacity, but sometimes people will use C for specific heat capacity. Sometimes people will use SH for specific heat capacity. I personally use S, and I think your book does as well, I think. But you will sometimes see a little bit of something else there. Now, if I have a high specific heat capacity for a substance, does that mean it takes more or less energy to change the temperature? It's a high value for specific heat capacity. It takes more energy, because that's what that number means. For example, water, it takes 4.184 joules of energy for every gram of water to raise it just 1 degree Celsius. So it's a lot of energy to do that. That's why people freak out when the water temperature of the ocean changes by like a really small amount of temperature, because it takes an incredible amount of energy just to move that much water's temperature by that little bit of a degree, right? So the larger specific heat capacity, more energy required to change the temperature of it. Smaller, less energy required to do so. Here's a table. Once again, definitely should know this number. And the reason why I say that's for liquid water, as you can see, ice is actually 2.03 and steam is actually 2, and those are all water. So depending on the state, it will have a different specific heat capacity. You definitely should know water's 4.184, and then also the 1 calorie per gram per degree Celsius. Although in our class here, we use joules a lot, but later on you may use calories, but a lot of times we do use joules. So you can see you can change the temperature of gold with a lot less energy than say aluminum. It takes a little bit more energy to do that. So let's try one here. Determine the amount of energy as heat that's required to raise the temperature of 10 grams of a sample of aluminum, specific heat capacity 0.89 from 25 to 58. Give your answer in joules and calories. So take a moment or two, see what you come up with here. Look here, since we're getting to the end. we want to use our specific heat equation, which is Q is equal to ms delta T. In this case, that is a mass. So we have the mass is 10 grams. We do have the specific heat capacity given to us, 0.89 joules per gram per degree Celsius. This is our initial temperature, 25 degrees Celsius, and that would be then our final temperature of 58. So we really do have everything we need. So we'll go Q is equal to 10 grams times our specific heat capacity, 0.89 joules per gram per degree Celsius. Once again, we want to do final minus initial. So this is going to be 58 minus 25 degrees Celsius. And if we do all that good stuff there, we do get an answer on our calculator of 293.7. In terms of units, grams will cancel, degrees Celsius will cancel, will leave us with joules. We also want to look at a little significant figures. What should it be? Well, this one's got 3. This one's got 2. And when we subtract this, we end up with like 33, right? Which is also 2, right? So technically speaking, we should end about there, which would take us to about 290 joules, which would be one answer. We also want to convert it to calories. So once again, 1 calorie is 4.184 joules. So we'll take this and divide by 4.184 joules is 1 calorie. Those guys will cancel, gets us about 69, I think. 69 calories. First off, any questions on the calculation? Is this exothermic or endothermic? It is endothermic. This is a positive number, right? And we see that by actually, in this case, the temperature, right? The temperature started at 25. So as it gains all that energy, temperature starts to rise. When we would have an exothermic process, our final temperature would actually be lower than our initial temperature, right? So as that substance would release the energy, its temperature would come down, which means its final temperature would be lower than its initial, and that would result in a negative value, and that would give us a negative Q value in that situation. So in this case, it is the temperature where we could kind of really see exothermic or endothermic. If the temperature rises, endothermic for that substance. If the temperature drops, exothermic is going to release that energy. Any questions on that there? All right, we're laid up there for today.